Mozilla for hosting us and feeding us and giving us beer. So before we start, we have just like one announcement. There's the Rust 2018 roadmap is up. So, and it's pretty interesting this time because we're going to be producing what we call an edition of Rust. You may have heard this term before as epoch or epoch or epic, or there are many ways of saying the word. One reason why we now call it edition. But so it's going to be, this year's going to be pretty interesting for Rust. We're going to see a lot of things landing. Check out the roadmap to see what we're planning. Hopefully we'll actually get there. And if you want to participate in making it happen, talk to me or talk to some of the people involved in 2018, and you can help. So today we have two talks. We have Tristan Hume from Google talking about algorithms in Rust, and we have Patrick Walton talking about Pathfinder. Jeffrey Seyfried was going to give a talk about procedural macros, but he's unable to come today, so we might see that later, some other meetup. And where Tristan? Yeah, there you go. And I'll hand it over to Tristan. Thank you.
Hi. So yeah, while I get my laptop intro, so I'm a UWaterloo student. I do a lot of internships. Currently, I'm interning at Cruise, but last time I was at Google, and I'm going to be talking some about the work I did at Google. Yeah, it worked correctly. So I'm going to be talking about algorithms in Rust, and what I mean by that is kind of a more general thing where I couldn't get the right word exactly, but I mean kind of the computational code, not the I/O code that renders things on screens or talk to servers, but like computing some quantity, kind of the code you have to think about a lot, often doing things on whiteboards. It's found in like programs to varying extents. Some programs are almost all algorithms, and some programs just have like, oh, this one function actually needs to do a bunch of things, but it's actually just this one corner of the app. And this talk is focused on these algorithms in Rust and what the Rust ecosystem offers. So what I'm going to be talking about is what makes Rust good for algorithms, tips for writing and testing algorithms in Rust based on my experience, and also some of my favorite Rust crates that I've found and used. So my personal experience with this is that I've done a bunch of Rust projects, and all of them have had some kind of algorithmic component. So the main thing is that I worked at Google on this conflict-free replicated data type for text synchronization with Rafe Levine. Doing a text editor, you could type on multiple things, and it would sync all your edits together and merge all of them and converge on one document that contained all your updates. I also wrote a syntax highlighting library for Rust that contains some parsing algorithms and highlighting matching, kind of like CSS, but a little bit toned down. And that's used by a few companies. And I also have some like smaller projects that one of them is like literally just an implementation of an algorithm and nothing else. And then a few of them are things that have like a core bit that contains some kind of algorithmic code. Some various notes about this. A lot of these things I'm going to talk about apply to like many languages, but not all of them apply to the same language except for Rust. Only Rust has all of these attributes bundled in one language. If you want to get spoilers or more likely click links, you can go to thume.ca/talks, and on that page there's a link to the slides. And also, all the code examples, at least for the first part of the presentation, are real code from projects I've worked on just because that's what I know. And so, why Rust for algorithms? First thing is just a simple thing. It's so easy to test. I find that when I'm writing algorithms, I often want to try it on a few examples, and normally in other languages I'll use a REPL or just like one-off code in my main function that I later comment out and then delete to test that it just works in simple cases. And in Rust, I find myself doing proper tests. Just because I don't have to set up a testing framework, it's already there, and it's so easy to use, and these become regression tests. Also doc tests. So if I'm writing a complex function that does some fancy computation, I can write documentation on how to use it correctly and what kind of data structures you pass as the inputs. And the doc test will actually check whenever you run cargo test that the documentation is up to date and compiles and works correctly. Another thing is safe refactoring. So when changing the implementation of a data structure, or like adding new cases, or like changing a certain algorithm that's just one component of a larger computation, it's great to be able to refactor things with confidence, and Rust's type system really allows that. And also the great compiler error messages allow just like a workflow where you change one part of your code and then you get a list of all the other things you need to change, and then you just go through those one at a time until you've updated everything that you need to update for your code to work. I often find that after I've done a big refactoring, I compile and it actually works first try, which is a attribute that I haven't had in any other language except Rust and OCaml. And the easy tests also help here too. Another thing, this is a like catchphrase of Rust's, fearless concurrency. And the way this applies to algorithms is that a lot of the time when you're writing computations, there's like simple things that are embarrassingly parallel, but they're not too important for the performance of your app. So most of the time you just write them as a serial for loop in most other languages. But Rust makes it so easy to do concurrency, especially with libraries like Rayon that give you these parallel iterators like you see on the screen, where you can just easily replace your for loop or iterator chain with a parallel one that uses thread pools. It just makes it like that much lower friction to make your algorithms parallel. Next is sum types. So these are like enums on steroids, and they allow you to create these great data structures that encode all the cases that you later want to handle in your algorithms. And so in this example, I have this enum that has 5 cases, and what I'm doing is I'm lowering it to another enum using pattern matching, this basic scope stack op that only has push and pop. And in a, say, object-oriented language like Java, I might encode this as like an operation class that has 5 subclasses, and then later on in my program, I dynamically know that only 2 of these subclasses will actually occur, and then like error if they don't. But that's much more brittle, and like I have to do more casting and things, and I have to rely on that not changing if I refactor something else. So it's much greater to encode that into the type system. Next is auto-derive. This is kind of like writing mini algorithms for you. There's a lot of things like comparing your data structures so that you can put them in trees, or just like check if they're equal for tests. In languages like C that don't have this functionality, it's really annoying to like just not be able to easily print or compare your data structures, but Rust allows you to easily derive implementations for this that are also efficient because they don't use reflection, they use code generation. One of the best is debug, which allows you to just easily print a debug representation of your data structures. You can also use your own custom implementations of it. You don't have to use the auto-derive. And so like if you have one where just the fields of your structure don't really belie what it actually is. So in this case, this scope struct is actually 2 unsigned 64-bit integers that like contain a bunch of bit fields. So that's not very friendly to just print out for debugging. So I have this custom formatter for it. And so this allows you to do printf debugging. And one of the great things that you can do with this that not everyone knows about is that you can add a hash to your format specifiers, and that will give you pretty indented printing. So this is what it looks like. There's the first one with the normal format specifier, and then that's the second one. And you can see that it has all your fields labeled nicely. Next, some tips and advice. So this is a more like general tip. And it's something that I found super helpful when I was working on Xi, which had a lot of existing complex algorithms. And that was what I started out, is to understand all the existing code. I started by refactoring it. And what that meant is that I'd read through the code, and every function I'd try and understand it. And if I spent a lot of time figuring out something and then finally figured out the core of what it did, I'd add a comment above it, explaining my understanding. And if something was confusingly named and like it was inconsistent with other places, I'd just rename it. Or if there was something that I spent a lot of time figuring out and then it turned out that, oh, I was confused about this because it's just like inefficient or broken, and I could just fix it immediately. And this is especially helpful if you can pair it with getting code review from the original author. So in this case, I could do all these changes, and then I could send a code review to Rafe and ask, like, does this name make sense? Is my understanding encoded in this comment correct? And And that was super helpful. And it also helps anybody who comes after you. Next is to isolate complex logic, and this is something that Rust is really good at. The type system allows you to abstract out parts of your algorithm much better than languages with weaker type systems, and also, even in cases where you could abstract it out in other languages, you might not want to because it would make your code slower. But Rust's use of LLVM's optimizer allows a lot of these things to be zero cost, which is really great. So I have an example here that you can't read at all. That basically, there's two functions here, and they both have a whole bunch of complex indexing logic. There's like two nested loops and a whole bunch of if-else statements and like breaks and continues. And I spent like an hour trying to understand these functions and didn't get very far. So I refactored them or rewrote them into these two functions, which actually fit on the screen. And like, if you thought about them for a while, you could maybe understand if you knew what the zip primitive does. And that zip primitive is what I created. That was the abstraction that allowed these functions to become simple. And the complexity didn't go away. Here I have another screen of code that you can't read. I was just able to abstract it out in a zero-cost way using Rust's iterators. Now, half this code is just boilerplate overhead for using iterators in Rust that's somewhat unfortunate and may be fixed in the future. But there's still some complex code here, but it's smaller because the operation I'm implementing is simpler. And also, it's easier to understand because you only have to like fit a small operation in your head rather than a larger operation. And I also use pattern matching to make some of the boundary case logic for what these algorithms are doing is iterating over two arrays of different sizes in parallel and producing a third array. So you can imagine there's all sorts of like out of sync index logic and like cases for like this array ended before the other array. And I made that all simpler by using pattern matching to handle that edge case logic in a cleaner way. Another kind of abstraction thing is that Rust allows you to write complex looping structures as iterator chains. And for some things, I find this easier to think about than a loop structure with a bunch of breaks and continues and ifs and things. Just like thinking of it as a data pipeline with things like filters and changes and find the maximum. And the great thing about Rust's implementation of this is that it compiles down to approximately the same thing that you'd have written if it was you'd written as a loop, which is really great. And in fact, often better than if you'd implement it as a loop, since a lot of these things can elide bounds checking, where Rust's loops with indexing can't. Next is kind of a opinionated tip, which is to the Rust borrow checker has trouble with cyclical data structures. If in another language like C++, you might have a bunch of structures that have pointers to each other, and like in a doubly linked list, they can maybe form a cycle. In Rust, you can't do that straightforwardly. The borrow checker will complain. And this kind of like belies some underlying memory management issues that make this really difficult to deal with even in C++. And there's a variety of solutions to this in Rust. And I'm going to come out and say that using a vectorino is the best. And what that means is that you create a vector, just an array, where every time you have a new node, you just add it on to the end of the vector. And instead of where you would normally use pointers, you use indices. And so to look up a adjacent node in your graph or your linked list or whatever, you just take the index and look it up in the vector, and that's your other node. And this has the downside that you have to pass the vector along with your node to a lot of your functions, and that is a real pain, I say. However, it solves a lot of the mutability and borrow checker and memory management issues associated with this, and you also get the side effect of your node allocation speed is good since it's the exponential resizing vector, and most of the time you're allocating it's just a pointer bump. And also, you can often, depending on how you allocate nodes, get data locality as a side effect of this, so your cache does better. So the alternative to this is, one of the main ones is reference counting with weak references to break cycles, so your memory management works out, and also a ref cell so that you can mutate things and form the cycles to begin with. And this can be a real pain. I used it in Syntect, my syntax highlighter, and I really regret it. It created problems with the API where, so in the specific instance, I have a syntax set that holds a whole bunch of syntaxes for like HTML and JavaScript and things. And then from that, you can extract a single syntax like HTML to highlight with. And the problem is people would reasonably think, oh, okay, I'm going to extract the HTML syntax, and then I don't need all these other syntaxes since I only care about HTML, so I'm going to drop the syntax set. And then you try and highlight an HTML document, and then it works perfectly fine. However, if you then add a script tag to your HTML document, the syntax highlighter then says, oh, I need the embedded JavaScript syntax. Let me open up this weak link and go get my JavaScript syntax. And then it panics since the weak link is empty since you've dropped the JavaScript syntax on the floor. So this is especially bad because it appears to work in initial testing, but actually doesn't and panics at runtime. And using an arena would have made the borrow checker stop you from doing this in the first place. Another thing that problem it led to is that it made some things impossible to parallelize. RC, Weak, and RefCell are all like very single-threaded. You can use arc to make your reference counting multi-threaded capable, but then to do RefCell, you instead need to use mutexes. And while I could have done that and just done the straightforward replace, it would have made the entire syntax highlighter like ungodly slow. So that just wasn't an option. And so basically there's things that like right now you have to duplicate all your syntaxes for each thread in your thread pool, which is not great. But fixing it would require refactoring all of syntax to use vec arenas. And also vec arenas have that passing it boilerplate, but RC, RefCell, and Weak have a bunch of boilerplate as well with like cloning, reference counting, and using these guards for the RefCell, and a lot of things that like were would have been straightforward indexing iterators became super inefficient things with a lot of like reference counting and guard manipulation, so that they weren't inlined anymore and this iteration was slow. I'll do questions at the end. And so that's like why I didn't use this. Or I did use it and I regret it and you shouldn't. Anyway, moving on to some of my favorite libraries. Some of these I've used and some of them are just things that I've seen on something like reddit.com/r/rust and checked out and read some of the code and readme and thought were really cool and starred them on GitHub for later use. And I got these by mining my list of GitHub stars. So the first category I'm going to talk about is property testing. And this is a thing where you can, instead of testing on a specific instance of your data, you can test on a generic, like, any data this property should hold. So in this first example, we have this prop that takes a vector of U32s, and we're checking that reversing the reverse of a list is equal to the original list. And what quick check will do in this first example is when you run cargo test, it will generate, say, 100 random vectors up to a given maximum size and run this property function, and if any of them fail, then it'll print an error to your console and tell you your test failed. And there's a newer, fancier version of this concept in Rust called prop test that's based on Python's hypothesis library that uses kind of a different approach to it, where quick check, the arbitrary instance logic is based on the type, so there's only one way to get an arbitrary vec U32, and you can kind of cheat around this by writing like a wrapper type that's like positive vec32, but that's like not great, and writing those is not great either, especially because quick check has this feature where it can reduce your test cases. So if something fails on some big random list, then it can do kind of binary searching logic to produce and give you the minimal case that will cause your thing to fail. And that makes it way easier to debug. However, once you start using these wrapper types, the reducing logic can often be like broken and not work as well. However, prop test takes a different approach with these things called strategies, where each thing you want is composed with these combinators so that it's always reducible efficiently, and you can tell it to generate exactly what you want. So they also have this fancy macro DSL for it that has special cases for things like strings. So in this example, using their macro DSL, we're saying that this string give it anything that matches this regex. And it won't just generate random strings and check if they match the regex. It actually uses the regex parsing library to like only generate strings that match the regex. And that way it can do this efficiently and like checks all valid dates like in reasonable amount of time. So that's a really cool library. Next is Fuzzing. This is like property testing on steroids. It uses instrumentation so that it can explore random cases more efficiently and find failures. Often random things won't hit cases in your code, so this was originally pioneered for use with parsers. So if you can imagine like a C parser, you're trying to like check if it has any bugs in it that cause it to segfault, and you're just giving it random inputs. Well, like you won't trigger any useful cases in your compiler, you'll just like hit a bunch of syntax errors really quickly. But what fuzzers do is they instrument your code and look for paths of execution that are being taken. And what they do is they mutate inputs based on that. So if it finds a new input that exercises a new path in your code, it will take that input and then mutate it slightly, hoping that it'll reach further down into that tree of logic. And this is really effective and has found tons of bugs in C++ code. And so there's been a bunch of these fuzzers written that are super efficient and very nice. And there's Rust crates that wrap them. They're fastest at byte buffers because that's what their fundamental working on primitive is. But all the Rust crates that work with them have this kind of wrapper that allows you to take the byte buffer and turn it into an arbitrary type, actually using the same underlying crate that QuickCheck does. So there's 3 crates for different fuzzers for this. Hong Fuzz, which is a wrapper around a fuzzer from Google, Cargo Fuzz, which is LLVM's libfuzzer, and then AFL, which is AFL, which is another popular fuzzer. One problem with these is that they don't integrate with cargo test like property testing libraries do. This is kind of due to how fuzzers work and how cargo test works. Fuzzers require a separate binary target that they can work on independently from all your other code. So they don't work properly in cargo test, which is a slight ergonomic hit. So my impression from reading all the code of the fuzzing crates is that Hong Fuzz RS is probably the one that you want to start off with. It seems to be the easiest, one of the easiest to use, and also one of the best fuzzers. It's cross-platform, and like it uses all sorts of nice instrumentation and things, and it's pretty simple to integrate as well. Cargo Fuzz is also a pretty good choice. So benchmarking. This is actually kind of built into Rust. It's built into Rust nightly, but it isn't stable yet. However, you can get the same functionality almost on stable with this bencher crate that you can install. And what this allows you to do is it allows you to create benchmark tests, which you run with CargoBench. And these have this kind of API right here, which allows you to do some initialization that's not timed, and then this b.iter function, it takes a callback that it'll call in a loop and measure how long it takes each time, or like measure how long a batch of running 1,000,000 of them will take or something. And then it will give you nice statistics about it. And another thing this library provides is this thing called test black box. So if you have a function that computes something and you don't want to benchmark doing something with the result, but you also don't want LLVM to optimize out all your code that like computes the thing. What you can do is you can pass it into this test black box function, which does nothing and takes basically no time, but it's opaque to the LLVM optimizer, so your code to compute something won't be optimized out. So if you don't use that, be careful that your benchmarks are still valid. So instead, just use that function. CargoBench CMP is a nice separate addition to this that you can get. It allows you to nicely compare different runs of benchmarks or different implementations of algorithms, and gives you these nice tables that show the speed up and difference in percentages and absolute time. And also, you can kind of see what CargoBench's default output looks like here. It's the first 3 columns, or the first 2 columns. And you can see it also has a feature where if you tell it the size of your inputs, it can calculate megabytes per second as well as nanoseconds per iter for you. There's a newer benchmarking library called Criterion that does fancy statistics so that you can do like a t-test to figure out if your new algorithm is statistically significantly faster than your old algorithm. And it can also generate these super fancy reports that have like interactive charts and things with HTML that can show you like the distribution of the time. So if you have like really bad tail latency or something, and it can also show you like the scaling curve of your thing. So in this case, it's linear, but if you had a quadratic algorithm, that might be like a quadratic curve. So for parallelizing, I already talked a bit about Rayon. It's a library that has these great parallel iterators, and it also allows you to access the thread pools more directly. And there's also this other library called Crossbeam that's kind of like a generic toolbox for multi-threaded code, and specifically it focuses on lock-free code. So it has a bunch of lock-free data structures like channels, queues, stacks, that kind of thing. But it also includes primitives for doing threading. So one of the useful things it provides is these things called scoped threads that are kind of like a thread that starts within a function and also ends before that function returns. And that allows you to use data that's on the stack without copying it safely. And it also includes a library for doing memory management in your lock-free data structures. So if you don't use a garbage collected language, this can actually be quite challenging. And there's all sorts of approaches for doing this. And they have a library for doing one specific approach that's fairly efficient. Another different kind of parallelism, is SIMD. It's these fancy instructions that almost all CPUs have nowadays that can operate on multiple things at the time. So for example, adding 4 floats together in one instruction. Your compiler, to some extent, if you set the flags right to optimize for your specific CPU, it will use these automatically in some cases, but it doesn't always pick up on it. So it can be nice to specifically optimize for this. Rest Nightly now includes access directly to intrinsics for this, which basically are LLVM things that basically get translated directly to the correct instruction. And there's also this really nice crate because the intrinsics can be kind of impenetrable and difficult to understand for a beginner to SIMD. There's this crate called Faster that provides basically the Rayon equivalent for SIMD, where you can take your iterator that does some numeric computation and turn it into a SIMD loop that will guaranteed be executed with the largest vector size on your platform. And it'll also do the code for you to like check the current CPU architecture and dispatch to the correct vector size depending on what instructions are available, which is often like a whole bunch of boilerplate to do if you write it manually. So this is a really cool thing that takes advantage of Rust's cool type system properties and things. Next, I'm going to talk about geometry, which is kind of like a sub-area of algorithms, but it's an important one. There's kind of 3 main crates that do geometry in Rust, and they basically differ by their levels of type safety. So CG Math is the closest to what you'd find in any other language. It includes your basic points like vector and matrix and all the operations on them and some helpers for things like rotation and generating rotation matrices and stuff like that. And algebra is kind of one step up. It's also a nice library since it has really nice docs and a lot of helpers for things like camera view matrices for if you're doing GL rendering or that kind of thing. But it also includes more types. So for example, instead of using a vector both for directions and transformations or translations, an algebra has a separate type for translation. And there's one step up in type safety, which is Euclid, which goes further and also includes the units in your types. So this is what Servo and WebRender use. And you can see an example here. Basically, you declare these empty structs that just encode like what your unit is, and then you can declare these typed points that include the space or size or whatever. And also your projection matrices you can type as transforms that go from one space to another space so that you can make sure that you don't accidentally render in the wrong space. And these kind of bugs can be especially insidious because like in a lot of cases your different spaces can actually be the same in some cases. So for example, if you have a layer space and a screen and a window space and you only have one layer that takes up the entire window, then those spaces are the same in the common case of your like test framework, but then like when you actually go to deploy it, it won't work properly. So that's like a nice handy thing. The downside is it's a whole bunch of hassle and like you have to do more typing and things like that. So it's a trade-off. Next is Cryptohashes. There's a kind of GitHub repository that includes a whole bunch of crates for various cryptographic hashes, all with pure Rust implementations. Not all of them are properly SIMD accelerated, but like they all work. And I mentioned these because cryptographic hashes are useful for a lot of non-cryptographic purposes. So I find myself using them like almost more than a lot of data structures that are taught in university computer science classes, just because they're so useful for things like distributed systems where you have a bunch of data and you want to, like, on 2 different machines, you can hash the data and get a easy identifier to send to each other to say, like, do you have the same data? And also for caches, you can make sure that your cache keys don't collide with very, very extremely ridiculously high certainty. And also, there's all sorts of other nice data structures that use cryptographic hashes like Merkle trees. So this is an example of using like one of my favorite crypto hashes, Blake2b. It's not like the most standard one, but it's good. And one of the reasons it's good for algorithm use cases is that you can choose the size of its output. So if you only need, say, 64 bits of collision resistance instead of 512 or something, you can ask it to only give you 64 bits. Whereas with other hashes, you might have to like get 512 bits and then just throw a bunch of them away. So that's nice. It's also very fast when implemented properly with SIMD. I'm not sure if the Rust crates do that. Kind of in the vein of hashing, there's faster Hashmaps. So Rust's default Hashmap uses a collision-resistant hash function, and this is so that you don't screw up things like web apps and network services, where someone can send engineered inputs that cause collisions in your hash table and cause a denial of service attack on your system, where your server will spend all its time like iterating over these hash collisions when it should be doing normal work or like quickly indexing a hash table. So if you don't care about that property, you can opt into a different hash function. Still with the normal hash table function, there's like a hidden type argument that's the hash function. And one crate for this is fxhash. It's used by Rust, C, and Servo, and it's much faster than the default hash function. So especially if you have hash maps and tight cache loops or something like that, it's useful. I used a similar library in Syntect, and it gave a good improvement. There's also IndexMap, which is a different hash map that kind of uses a different structure that allows you to do fast iteration. And also it maintains insertion order, which is a nice property sometimes. It maintains insertion order provided you don't do certain things. Like I think you can't delete elements. This is just some other handy data structures. Slice DQ is a cool thing where normally if you're doing a ring buffer for a queue, you have this problem where you can't get a slice of its contents or any part of its contents because it might be in 2 discontiguous regions of memory. And Slice DQ solves this by taking a region of memory of physical memory and then using virtual memory to map it twice directly adjacent to each other. And then this allows it to give you slices that allow you to access your ring buffer with a contiguous slice while still being efficient and using memory in like such a way that it doesn't have to allocate, which is really cool. There's a lot of libraries for this in other places, and this idea is like used in like streaming libraries forever and things. But Rust is nice in that like it allows this to be safe, and it's an easy to use library that you can integrate with your system without much trouble. Slab is kind of a thing for doing the Vecurina pattern, but where you want to like allocate and deallocate nodes on the fly, kind of like an object reuse pool like you might see in Java for avoiding the garbage collector. Aluru is an least recently used cache. It's just a really simple library for doing like fixed size caching, just a handy thing. Priority queue, it's just a priority queue data structure. It does allow changing priorities, which is something not all priority queues allow. This is just my miscellaneous grab bag of libraries that I couldn't fit in elsewhere. Rust Pretty Assertions I really like. It's just a thing that you include in your project, and it makes all your normal assert geeks now show pretty diffs on failure. So if you have these big data structures that you're comparing, it will now show like exactly what differs between the correct output and your output. And it's also colorized for your terminal. Pest is just a nice parser generator. SIRD, a lot of people know because it's super important, and it's also like awesome. It solves all your serialization problems in like tons of different formats, and it does it all quickly, and it can automatically derive serializers for your data structures. Bin code is the thing to use with Siri. It's just a simple binary serialization format. It's used in WebRender for IPC, and it's quite fast. And so it's good for like storing large data structures in a fairly compact way, and like things where you don't care too much about interoperating with the outside world. Iter tools just allows you to like make your iterator chains more fancy. It includes more of these like fundamental loop algorithms. It's kind of modeled off of Python's iter tools library. Differential data flow, I kind of threw this one in for fun. There's this guy, Frank McSherry, who makes this thing where it's kind of like this platform for doing incremental computations across multiple nodes, and it like magically distributes all your stuff and like makes it so that when you change your input, it does minimal amounts of work. And he has all these benchmarks of him like this framework beating the pants off all existing graph databases with like, oh, I can do PageRank on these enormous graphs of the entire internet on my laptop, and and like if I change one link, then it all incrementally updates the whole thing, which is something that Google didn't do until like 2000 and something. So that's like a really cool library. The catch is it's really difficult to understand. The primitives themselves are simple and his code examples are short, but like understanding how they work and what those primitives do is quite the task, and I have tried like 3 times unsuccessfully. However, it is possible. There is a company named Eve that is now defunct, but before they died, they wrote a Rust implementation of their database engine, or their language interpreter, which is kind of a database engine, and it was absurdly faster than all their previous things and fully incremental. And it also was, since it was kind of a database engine, they could compare it on existing database benchmarks, and it beat the pants off of all existing databases that they tested it against. So there's a lot in here if you can understand it. So I encourage you to try and check it out and see if you get further than me. And apparently Frank McSherry has said something on Reddit. I saw a comment of his that was like, I don't expect anybody to be able to understand this without talking to me, so please talk to me. So maybe that's what I did wrong. Anyway, that's my whole talk. Hopefully you find some of this useful. So now, does anybody have questions? I know you had a question beforehand. Yes, that's a microphone. No. Okay. Just talk loudly.
So you were talking about the Arena pattern.
Yep.
Is there a standardized technique for making sure that you don't use the wrong index into the wrong vector?
Yeah. So I find that most of the time, like this, there are libraries that encode this in the type system. Can you repeat the question? Oh yes. So the ask was, is there a way to kind of like make sure that you don't screw up your indexes between different data structures and like use the wrong index with the wrong vec? And the answer is yes. There's libraries for this that kind of like are generic graph libraries. They do this and encode it in the type system properly. However, the catch is that they're often I find they're more trouble than they're worth. They're probably a good idea if your cyclical data structure is literally a graph, like it's a sea of uniform nodes that all interconnect with each other. They're better for that pattern since there's libraries specifically designed for graph that even have graph algorithms built in. But in my case, like my thing wasn't precisely a graph. It was just like a bunch of data structures that were all different and happened to have cycles. Like I had syntaxes which contained rules, which contained this, which contained that, which then had references to other syntaxes. So like there I like most of the time was using normal things, and then sometimes I had a reference that could be cyclical, but I only had one type of thing in my entire program or library that was cyclical. So in that case, like indexes probably would have been a better bet. But yes, if you want to encode it in the type system, there are libraries for doing this.
So actually, is it working now? You might need to talk more into it. Test. No. It was working. Yeah, it was working when you tapped it. Okay.
Talk louder.
It just doesn't like you. Just repeat the question, I guess. So. Related to the previous question, why didn't you just use the Arena crates?
Yeah, so that's one of the crates that I was talking about. the arena crate is the question.
Typed arena.
Yes, typed arena is one of these crates that does this. And, well, like, the simple answer to the direct question of why didn't I use the typed arena crate is that I used RC ref cell and I totally regret it. But, like, if I was to start again, I wouldn't use it because basically it wouldn't add much value to me and it would add a slight amount of complexity. Because I have this, like, basically I don't need anything it offers. I only have one type of cycle in my entire data structure or in my entire library. So messing up indexes is not too much of an issue. And like passing an arena is not that much like harder than or easier than passing a vec.
Right, it's exactly the same.
Yeah, so basically like I could use typed arena very easily and it wouldn't make it any worse. Basically, but like, yeah. So typed arena would be just fine. And the only reason I wouldn't use it is that it wouldn't add very much, so I wouldn't bother to like include it in my cargo.toml, do the very minor amount of work there. Yeah. Other questions?
It's working now.
Oh, it's working now? Allegedly?
Allegedly.
Yeah. Okay, thank you. I was just curious about what you found was really useful in teaching effective design of when you design the programs. Because I noticed over time, like working on these projects, like Rust is one of those languages that responds really well to seeing examples of good code. It's a lot like painting or something, or like drawing. Like you go make way more progress when you see other people doing well, as opposed to just like kind of going on your own, just duct taping everything together.
Let's see if I can come up with a good response for that. I think like I do see what you're saying. One thing that's I find nice about Rust is that like it is easy. I find myself facing less trepidation trying to understand existing algorithmic code. Like in the Xi editor, like there's these fancy rope structures and things, but like the type system and like the structure that provides and all the other things I've talked about really allow me to like understand things better. And also like so in my Xi work, near the end of my internship, I wrote up a big, huge document about all my work explaining like the algorithms and things. And that's online if you like look under the Xi editor repo. It's in the docs thing. It's called like CRDT details or something like that. And it has a bunch of diagrams as well. But like I found that Rust was actually useful for that since I could explain a lot of the data structures just by copy and pasting the Rust struct definitions into my document. And that was like a good like teaching mechanic where like before I explained the implementations of things, I could still like reference the data structure beforehand. And that gave you a surprising amount of info required to understand the system. So I hope that's like somewhat relevant to what you were talking about. Any other questions?
That's great. Thank you.
Anyone else have their hand up? Nope. Okay. Well, thank you.
Next we have Patrick on Pathfinder. Should be a shorter talk.
Yeah.
Well, no, keep this here.
This one's going to be short because I was told at about 3 p.m. today that I would be giving the talk. Nice. Okay. All right. Hey, everyone. I'm Patrick Walton, PC Walton. You may know me on IRC, Twitter, Hacker News, wherever. I'm at Mozilla Research, and this is a talk on Pathfinder. Some of you may have Pathfinder 2 this time. Some of you may have seen my earlier talk on the first version of this, and since then I've been working on improving it. It's almost all completely rewritten since then, and I'll actually have some demos to show for you this time. So for those of you who don't know, Pathfinder is a project that has that's designed to be a GPU renderer for vector arts, including fonts. So that's SVG, HTML canvas, fonts, you know, so the applications like maps and graphs and all sorts of other things. There's actually, I don't have it on the slide, but it's actually expanded to the 3D space now. So we're doing work on putting vector graphics in 3D. Obviously, this is interesting in VR. So it's basically an all-in-one vector graphics toolkit. And it's written in Rust and OpenGL. And I have a sort of demo and testing framework that I wrote in TypeScript that runs in the browser, so you can actually try it in the browser. If you have a JavaScript app, you can actually integrate it. But it's all Rust, but all of the CPU side work is basically all in Rust. So the question I always get from people who have looked at this stuff is, you know, how does it differ from signed distance fields, or how does this differ from Slug? Other projects you may have heard about. So I'm not going to go into too much detail here because this is kind of graphics nerd stuff that, you know, no one really cares about, but maybe two people in this room care about it. But basically, there's kind of a taxonomy of different approaches. There's texture-based, where you do a whole bunch of CPU-side work and kind of render. It's texture-based approaches are basically kind of rendering on the CPU to some sort of scalable thing that you can then zoom up, and you can zoom in and zoom out without having on GPU to some degree. So there are several approaches. You may have heard of signed distance fields. There's one called Slug that's been going around lately that is also in this family. There's a blog post by a guy called William Dobby who has an approach similar to that. So Pathfinder is not one of those approaches. Pathfinder is actually is designed to do the maximum amount of work on GPU. So it actually uses all of the GPU hardware. It doesn't really have much of a CPU component to it. So there's basically two modes. And this is kind of, one of the things I discovered is that there's actually really not one-size-fits-all approach to rendering. There's a trade-off between how much CPU work you want to do up front and how fast you want the GPU stuff to run. So actually this is, Pathfinder allows both. So you have a mesh where you actually you convert the vector art into simpler curves that the GPU can directly draw. This is a CPU prepass that takes that does take some time, but it's n log n, so it's in the number of vertices, so it's actually pretty fast. And it doesn't have as much, it has the minimum amount of GPU work at runtime. So this, usually you would use this for SVG, you know, if you had things like maps where you want to do more work ahead of time in exchange for faster GPU time, then this is what you would use. And this is totally scalable. Once you've generated the mesh, you can render it at any resolution. You can zoom it up, zoom it down. And I have some demo that I'll show after this. The other approach is it's called stencil and cover. I took that name from NVIDIA's work on NV path rendering, where you actually just take the vector description, the path, just upload straight to the GPU and go. This is slower because it has more overdraw. It's drawing more on the GPU. But oftentimes for small fonts, this is really what you want because the GPU is so much faster than the CPU that you just want to get it over there and go. It doesn't matter whether it's as fast as theoretically possible. So for font rendering, one of our goals, one of the main goals here, since this is going to be used in web render, so in Servo and actually in Firefox, I can't, there's, you know, I don't have a release date for this stuff, but I have screenshots later of, I actually have a build of this running in Firefox. And one of the most important goals here is to closely resemble the native OS font appearance as much as I can. So I'm not going for pixel perfect accuracy. You know, nobody would be able to notice the difference, and it would be a whole lot of work for no real benefit. But I am going for, basically, it won't look, the fonts and text won't look out of place. It'll look like any other native app, and it'll look and feel native, except that it should hopefully go faster. So there are all these features that it has that the native OS font renderers do. It does subpixel anti-aliasing. So this is where it kind of triples the horizontal resolution effectively by using the the individual colors on the LCD screen to kind of get a sharper look horizontally. It does gamma correction for people who care about that. It does stem darkening, which is a thing where it actually makes the fonts a little bolder to make them easier to read. Mac OS does this. It'll do hinting, and it can do some nice sort of special effects, like making fonts bolder automatically, making fonts narrower automatically, rotating them. It can do all sorts of things. So this is just a simple graph that I have. This is actually an older one. I've actually gotten a little faster since then. But you can see lower is better here. This is Nimbus Sans is basically Helvetica. It's rasterizing all of the Latin letters, so A through Z, uppercase, lowercase, and you can see the font size. As font size gets bigger, obviously it takes longer to rasterize, but the GPU scales much better. As the font gets larger and larger, the CPU just gets slower and slower and slower, whereas the GPU barely breaks a sweat. And this is actually on the integrated GPU. This is not on the higher end GPU. This is on the lower end Intel GPUs that you basically can't buy a CPU from Intel without having one of these in it anymore. So this is obviously a very nice improvement, and you can sort of see how this could be useful when you're doing pinch zooming and other applications. So this is new. Some of you may have seen me tweet this screenshot. This is I have a local build of Firefox that actually uses Pathfinder to render all the fonts. So if you may be looking at this and saying, "What's the big deal?" This is just a screenshot of Firefox. Exactly. This is Pathfinder rendering all of the Pathfinder's actually rendered all of the glyphs in this on the GPU using WebRender to actually render the rest. So that not only the page but also all the UI of Firefox is rendered with this too. So if you haven't tried WebRender in Firefox Nightly, give it a try. It's you can just Google for how to use WebRender in Firefox Nightly. It's coming along really well, and hopefully Pathfinder will be an optional component of that soon. So WebRender probably, the first version of WebRender probably won't be using Pathfinder because we have enough GPU bugs as it is. We don't want to roll a huge amount of stuff out at the same time, but hopefully Pathfinder will be following suit soon thereafter. So next steps for Pathfinder, fixing bugs, completing testing infrastructure, documentation, simple usage examples. We need, I want Pathfinder to be a thing that's really easy to integrate into your project. I kind of want it to be a vector graphics toolkit. If you need to render SVG, if you need to render fonts in your project, Pathfinder should be the thing that you go for. And there's some theoretical work to do too, well, more theoretical-ish work to do too, improving anti-aliasing for SVG. We have anti-aliasing for SVG, but it's not quite at the level that I want it yet. There's just more work to match the native fonts, match the native font rasterizer, especially on Windows, which does a lot of hinting. So hopefully this will not succumb to the demo curse. So this is actually a web app that I use for testing Pathfinder. And this has been really, really helpful because, I can kind of get live feedback. Also, you can take this code and use it if you want to use this on the web. This is not live yet, but I am hoping to have it up soon. So you can see that the pinch zooming works. This is all rendered in real time. You can do rotation. Yeah, and this is, all at high frames per second. You can actually mess with the boldness, making things thicker if you want. You can play with different fonts. Takes a little while to load the font because it's actually doing this on server. Maybe I need to reload. But anyway, so another thing is SVG. You may have seen this picture. It's a common picture. You can actually zoom it, look around, rotate it. I say that my day job is like mostly spinning pictures of tigers around, because it is. So yeah, this is, as you can see, it works with SVG. So yeah, thank you. I don't, like I said, I do not have that website up yet, but hopefully I'll have it up soon with that live demo. And you know, my goal here is to make, again, to make this really a vector graphics library that is kind of a go-to vector graphics library. So if you have any feature requests, things that you want to see in a vector graphics library, you know, if you try it, doesn't work for you, it's slow, please file bugs. And thank you. So any questions? Let me.
It's okay. It's fine. We drank them all. It's fine. Yeah, we like ate everything. It's cool. Hello. I survived that. All right, cool. Yeah, so if you're using Pathfinder in like a UI layout engine, does it handle like rectangles? So like, will it not compute the SVG stuff that's outside the clip rectangles of the SVG views in your layout? So if you have like a bunch of SVGs that you're rendering, but you only have small windows into them. Like,
oh yeah.
Yeah. So,
okay, yeah. So that's one of the things that the mesh is designed to do. So really, the mesh sort of uses the GPU hardware as much as it can for the rasterization. So that's one of the things it'll do. It'll do clipping. It still has to transform the vertices, but in general, it will not render any pixels that are not seen. One of the reasons, it also does this for Z-calling. So one of the reasons the Tiger goes so fast is that it doesn't paint any pixels you can't see. So, you know, like there's actually a whole lot of background stuff that's covered up by the stripes. It doesn't paint any of those pixels. It only paints the stuff on top. And that's actually sounds really hard, but actually all it is using the GPU hardware which already exists to do that.
So, but is it still submitting the vertices that are outside your clipping regions to the GPU, though?
Yes,
like
it
before
is.
That? Okay.
You could, and for maps, you probably would want to, you know, divide your scene up into sectors or something so that, you know, you only submit the vertices because, there's only so much, it's kind of a catch-22, right? You want to have, you need to know the transforms to do that, but you can only do the transforms on the GPU. So it's not really a one-size-fits-all situation. You might have to do a little more work to reduce the vertex shading time. But in general, you know, it uses the hardware as much as possible. And you can, of course, layer things on top of it.
Thank you.
Back there, I guess.
I was kind of curious, what was the hardest part you had in, I guess, like maintainability? Like in terms of testing or creating documentation that was like really concise or clear?
Are you asking what the sort of hardest part of testing this has been?
I'm making something that other people were comfortable using, because a lot of the elements of making an external facing library is making it understandable for people and reliable. So there's testing and then there's documenting it.
Yeah, I mean, certainly that's an ongoing challenge. I know one of the biggest issues here is I don't have nearly as much documentation as I want. I'm still doing some, you know, I've still been doing some experiments. The API's been changing a lot. So I can't say I'm doing a very good job of it at this moment. But, you know, going forward, especially around fonts, it's stabilizing. This is pretty much the approach that I know I want. So I know that one of the most challenging things here has actually been to get something portable and that works for all use cases. So, you know, there's all sorts of different use cases for for rendering text. Some people want to put it in 3D environments. Some people want to put it, you know, just render it on screen. Some people care about some pixel anti-aliasing. Some people don't. Making one API that works for all of these use cases is tough. And so, you know, I've had to do several kind of redesigns, and it's kind of in progress right now. But I'd say that's definitely the hardest one, making something that's flexible enough for everyone's use cases. I don't know if that answers your question, but
It does. Thank you.
Great. Or over there, I guess just.
Where?
Yeah, for Rafe, I guess. Just kind of going around this way might be easiest. Or maybe not.
So a while back, we had a talk at this meetup about Alacrity, a really fast terminal emulator.
Yeah.
My question is, how fast would a terminal emulator that uses Pathfinder for rendering be?
I don't know, infinitely fast, light speed. I mean, really, it depends on. So the glyph cache hit rate. So the thing Alacrity does is that it caches bitmaps of all of the glyphs, right? And because it's monochrome, monospace, it's particularly easy to do that because your hit rate gets even higher because you don't have like subpixel stuff to worry about. So basically, it depends on a lot of things. If you're talking about, if your glyphs are already in the glyph cache, if you're just talking about, I've already got like all of the glyphs that I'm going to render, like you're only using Latin alphabet, right? And you've already got them all in the cache. Well, then Pathfinder will make no difference at all because they're already all cached. However, if you were in a situation where you were doing like zooming, I don't know if you would want to do that on a terminal, but maybe you would. Or if you had CJK, Chinese, Japanese, Korean, where your glyph hit rate will not be as high, then you could start to see some nice improvements. It really just depends on how often you're hitting that cache. Really, the reason people have been getting away with relatively slow glyph rendering so far is that the cache hits rate, that you can kind of put a cache in front of it and nobody notices. But when you start having things like zooming, then that breaks down. So I guess to answer your question, it totally depends on the workload. Under a common workload, I would not expect it to make much of a difference. Under less common workloads, it could.
On your web-based demo, was that Rust compiled to WASM?
Yeah, so that's actually, I originally tried that, but I actually did that way before that was stable, and so it was like, I didn't get that working. So what I actually do is that is actually a Rocket web app that does all of the Rust work server side and sends the raw GPU buffers to the client to be rendered. And this actually dovetails, this sounds crazy, but it actually had a very nice sort of second outcome, which is some people don't want like Rust dependencies at all. And this actually is something that people can use. So I actually have a tool that will take a font and given a subset of glyphs from the font, will pre-bake a whole bunch of Pathfinder meshes and just write them into a file using the same code that I used for that demo. And then you can use Pathfinder without having any of my Rust code at all. You just literally upload that to the GPU and use my shader. So this is actually, I imagine that this would meet the needs of game developers, people like that pretty well, who may be wary of external dependencies, whether Rust or not. So it actually had kind of a nice side effect doing it that way. I really would like to try having... I really would like to try the WebAssembly thing again, though. Now that it's more stable and that people are actually playing with it, I would like to give that another go. But for now, it's just kind of server side.
Cool, thanks.
Mm-hmm. It does. Well, more or less. Yeah, you may have seen this thing outside. Yeah, these are the actual names on it. Yeah, so this is obviously the kind of thing that I show to people who are interested in using it for VR. So you can use this in 3D. We actually do have a VR version of it that Manish has been working on. So it doesn't look wonderful right now, but we're working on fixing the issues, and we're pretty confident we can get them down. So yeah, stay tuned. Mm-hmm.
Without knowing anything about the various formats, how much more horrible is PDF than SVG? Like, how big of a leap would it be to use Pathfinder to render PDFs?
I actually think that most of the difference is going to be the stuff that isn't the raw vector graphics rendering, like the parsing and PDF is kind of like a PostScript-y thing. And it's not PostScript, but it's PostScript-ish. I think it's not really any more difficult than SVG mostly. I mean, SVG, earlier versions of SVG, you know, were pretty simple, but now SVG has all sorts of features, and so does PDF. I'm sure there's some work to do around the edges where you'd have to add some stuff. I should actually mention that a non-goal of Pathfinder right now is to actually support all of the fancy effects that are possible in SVGs and PDFs. Well, especially SVGs, because WebRender does those, and they're really kind of outside the realm of vector graphics. Like things like blurs. Like blurs aren't really vector graphics. They're kind of, you know, like just special effects in general, and you can put those inside SVGs. So my thinking right now is that most typical SVGs that you will see, you'll just need Pathfinder. For fancier SVGs, you'll probably want to upgrade to using WebRender, which knows how to do all the effects and stuff, and integrates with Pathfinder. In fact, that Firefox screenshot was going through WebRender. So I am not an expert on the PDF format. I've looked at it. My sense is that it's about the same as SVG once you've gotten, you know, a library that can convert them into that can sort of, you know, boil them down into more or less the same format. Someone who is more of a PDF expert can definitely correct me though. Yeah.
How soon might we see this powering Canvas?
How soon might we see it powering Canvas? I am hoping. I don't know. Help wanted. Really, it's doing Canvas with this is certainly a goal. It is. I think with all of the special effects that Canvas provide, you probably actually want to hook this up to WebRender and not Pathfinder, and not just Pathfinder. But I don't know. I can't give dates, but it's certainly something that we would like to do. Okay.
So what is Pathfinder doing differently in the 3D case? Like, is it not just a different view transform, like on the same glyph output? Like, are you sending already transformed vertex buffers or something, or like?
Yeah, it's not. This is using the mesh. It's not using stencil and cover. So as I mentioned, Pathfinder has two modes. It has mesh and stencil and cover. The text that you saw earlier in 2D was actually stencil and cover. This is the mesh, but other than that, there's no real difference. Okay. This doesn't have the subpixel anti-aliasing and stuff because that would look weird in 3D. But yeah, it's basically, it just kind of works, and that's a design goal. Especially CSS, keep in mind CSS is 3D also, so it has to support that in order to really work well on the web.
So the difference is that traditionally you would be rendering fonts to a texture and then rendering the texture off that frame buffer on the cube, but over here you're actually placing them directly.
Yes.
In 3D.
Yes.
Okay.
There's actually this demo right here is actually a little bit of both, depending on how close you are to the.
There's like MIP mapping.
Yeah, it's basically manual MIP mapping. So there's there's a little bit of cheating going on to reduce the vertex count, but that's basically the idea. Again, there's no one size fits all solution for this stuff. That's one of the things I've learned. There's no magic bullet. So, really, what does well for text at small sizes far away in 3D may not be the best approach for text highly zoomed in 3D.
It's pretty awesome.
Anything else?
Ready?
Let's not break anything.
Back to the PDF thing. Have you tried just opening a PDF in your Firefox build that has Pathfinder? Because PDF.js should take care of all the conversion, right?
Well, PDF.js is Canvas.
Oh, okay.
Yeah, and I don't have right now. Canvas goes through Skia even in WebRender, so that would be the way I would test it first, obviously, because I'm not writing a PDF reader from scratch. Yeah, so I think really to test PDF, you would want to go through PDF.js. At least that would be the fastest route to the solution. So really, it's kind of just blocked on the Canvas backend.
What caused you to write Pathfinder 1 into Pathfinder 2?
Oh, that's a good question. I probably should have mentioned that during the presentation. basically, Pathfinder, one of the main goals of Pathfinder 2 is to scale down to low-end hardware. In fact, I believe if you have a GPU manufacturer since 2002, you can run some variation of Pathfinder. Simply because Pathfinder 1, on the other hand, was tessellation shader. It used tessellation shaders. It used compute shaders. It really required sort of the highest end graphics, and WebRender in particular targets OpenGL ES3. So that was a mismatch. And another reason is for part of this, or this kind of illustrates the other reason. I found that there's, again, no one-size-fits-all approach. Pathfinder 1 had really a stencil and cover kind of method. It was I guess, summed area tables, and which effectively works out to just a variation of a stencil and cover method, which works well for text at small sizes, especially. Also works well for very dynamic paths, but it doesn't work as well for cases like this, where you have, in a 3D environment. It doesn't work as well for multicolor, where you want to use the GPU hardware to eliminate overdraw. So I really wanted an approach that could, a hybrid approach. I found that a hybrid approach was really the best one. So I guess that's the other reason. So it's really wanting to support a hybrid approach well, and wanting to have lower end hardware support. So to be clear, I don't mean to rule out using new OpenGL features when they're available. But with Pathfinder 2, I'm starting at the bottom and working my way up, which I think is a good situation to be in. Anyone else? Yeah.
How much work does Pathfinder do around glyph placing and what I'm trying to ask is, how low level is it?
Yeah, okay. So that's actually an interesting question, because the Pathfinder right now is quite low level. Like, it takes glyphs. It doesn't know anything about characters. It only knows glyphs and absolute positions of glyphs. However, one of the things, I sort of I've been doing surveys trying to figure out what people want from a vector graphics API. And one thing people keep saying is they don't just want a font renderer. They want text. They want a text renderer. They want something where you give it a string of text and a rectangle and say, draw this in this rectangle. So I've really been giving thought to how best to integrate Pathfinder into something like that, into an easy-to-use solution that does the shaping, the layout, and the low-level rendering. So right now it's the low-level rendering, and I'm not going to be rewriting all that stuff from scratch. I'm not writing Harfbuzz from scratch. That's a little bit. It's this has taken long enough, but as to making it easy to integrate with that stuff and sort of having an all-in-one solution that's very easy for people to use, I think that's going to be important. And so that's something I'm going to be looking into in the near future.
Just a short follow-up on this. Do you consider this as something that should be a feature of Pathfinder, or shouldn't something like layouting or ligatures or text layouting be a feature of a higher level API or a higher level library that should handle this?
Yeah, my general thought is that it should be a higher level API. Right now, Pathfinder is actually pretty modular. It's, in fact, Pathfinder is built on Lion, which you may have heard of. It's a low-level Bezier path manipulation library written by my colleague Nikal, and so I can see Pathfinder. I can see a higher level API being placed on top of Pathfinder. I don't know. Really, it's kind of a question of whether that API would go in the same repo, because Pathfinder itself just has a lot of little different crates that you can use. You can mix and match. So it'll definitely be a separate library. Whether it'll live in the same repository, I don't know. Again, this is just very early sort of thoughts on how to do this. Anything else? All right, well, thank you very much.
Again, thank you all for coming. Thank you to both of our speakers. Hope you come again next time. Since we've had just one major talk and one shorter talk, we'd have a lot more time to hang out and talk around if you want. As always, if anyone has suggestions for talks at the next meetups, please let me know or talk to Boats. Thank you.